Talk about some recent developments in non-convex optimization. So this might be a little bit to the side of the interests of people there. I'm not so sure of your background. So I put in some slides at the start to explain what, the basics of what's going on. So hopefully you can at least get a little bit out of it. So this is joint work with two of my former postdocs, or one current postdoc, one former postdoc, and a grad student, Michael O'Neill. So I'll give an introduction first, and then I'll talk about issues of convergence and complexity in optimization. What do I mean by those terms? And then this issue of escaping saddle points. We talked about this yesterday, that in non-convex optimization, you can get stuck at a point where the function is flat, but it's not a minimizer, because if you go in a certain direction, you can continue to go downhill. So I'll talk about that. I'll talk about first-order methods. These are methods that just use gradient information. They don't use the Hessian or second derivative. And then I'll talk about an algorithm that was proposed about 12 years ago, cubic regularization, and then say a little bit about these classical methods, line search, trust region, Newton's method, and I'll explain what those are in a moment. And then say a little bit about extensions to problems with constraints, which is quite a lot more difficult. Okay, so first of all, the context here. So for many years, when optimization was being used in machine learning and statistics, people focused on convex problems. And so, Steve Boyd has this, and Lieven Vandenberg, they have this big book from 15 years ago, Convex Optimization. And Boyd would lecture about convex all the time, and still does, really. And that's because there are many problems in this area that are convex, many interesting problems, like linear SVM, linear least squares, logistic regression, both the binary and the multi-class problem are all convex. And then if you do things like matrix optimization problems with nuclear norm regularization, that's also a convex problem, okay, as we talked about briefly yesterday. So there's a lot of interest in convex optimization. But recently, maybe in the last, 5 years or so, there's been a lot more interest in non-convex optimization, and that's because there are also many problems in learning, particularly large-scale problems, that are naturally non-convex. And the most obvious case is neural network training. Is almost always a non-convex setup. In fact, it's also non-smooth these days as well. And then matrix optimization problems, if you formulate the matrix, instead of using an entire matrix as the variable, if you form that low rank approximation explicitly, like the LR transpose that I talked about yesterday, the product of two skinny matrices, then that's a non-convex formulation. It's no longer convex. So we have to deal with that. The same thing in tensor factorization. There's more interest these days in tensors, which are like matrices with more than 2 dimensions, 3 or 4 dimensions. There are lots of interesting data science problems with that structure. And if you're looking at low-rank tensors, again, you tend to get non-convex problems. Non-convex regression, we talked about that yesterday, these extensions of least squares where the loss function, instead of being a squared function, it flattens out at a certain point. So it looks like a square, and then it asymptotes at some constant value. So that's also non-convex. And then nonlinear least squares, just classical least squares where the function is nonlinear in the variables is also a non-convex problem. Okay? So I'll just say a little bit about the main approaches for solving non-convex problems in the unconstrained case. That's where you just want to minimize a function f, which is a smooth nonlinear mapping from Rn to R. Okay? So all of these methods generate a sequence of iterates. So they have a sequence of guesses. You start at some initial point, and then the algorithm tells you how to construct the points one at a time. And hopefully they're approaching a solution. Okay? So first of all, line search methods. So these are methods that, first of all, they choose a search direction, dk, same dimension as x, and they take a step along that direction, say of length alpha k. And so there are many different ways to choose the dk. The classical way, which I'll say quite a lot about in the next few slides, is just to take dk to be the negative of the gradient of f. And that's guaranteed to be a downhill direction. It's guaranteed to improve f if you take a small step in that direction. In fact, it's the steepest direction of descent. It's the one that gives you, as a function of the length that you move along that direction, it gives you the most rapid decrease in f. So it seems like an intuitive good direction to take. But often people don't just use that direction, but they apply some scaling to the gradient. So the classical way to scale it is to actually take the inverse Hessian and apply that to the gradient. And that gives you Newton's method. Newton invented this for the case of, I think, scalar polynomials. But now people do it for large-scale general nonlinear functions, but he still has his name on it. You can show for various reasons that this has very good local convergence properties. It converges very rapidly when you get close to a solution. And then there are these quasi-Newton methods, and they try to imitate Newton's method, but they avoid calculating the Hessian, because that's a big n by n matrix of second derivatives. And it can be very expensive to calculate explicitly. So they use this an approximation HK to the Hessian. And they have very clever ways of updating this approximation. And the one that's used most these days is LBFGS, limited memory BFGS. Okay, and that's a method that it tends to be better than steepest descent and doesn't use very much storage. Okay, so another thing people do is just to apply some diagonal scaling to the negative gradient. So the atom method is a little bit like that. The atom is for stochastic gradient, where you're just working with an estimate of the gradient, but it also applies the diagonal scaling, and that tends to help. Okay, and you can do that here as well with a full gradient. Okay, so that's the first class of methods, and I'll talk mostly about line search methods in this talk. But there's a very clever variation on this called momentum type methods, and the famous Nesterov accelerated method is one of these, and conjugate gradient is another one. I'll talk about that more in the next slide. So momentum methods, you don't just take a step in the direction dk, which could be a negative gradient again, but you also add on a component of the previous step that you just took, the one from xk minus 1 to xk. You continue to move in that direction, but you make a small modification to bring in new information from the negative gradient. So that's the alpha k part of the step. Okay, so this idea is very simple, but it turns out to be improve the convergence properties quite significantly, both in theory and in practice. Okay, and the theory is quite complicated, but you can also get some insight into how it works in practice, because if you're always stepping in the negative gradient direction, it's very unstable. That you tend to get methods that zigzag a lot. Whereas if you do this momentum, it smooths out the steps, right? You sort of average over all the steps that you've taken, and just at each iteration you bring in a little bit of new gradient information. So it tends to give you search directions that are much more better aligned, and they tend to approach the solution in a more stable way. So it's a very powerful idea, momentum. Okay, and then there is the trust region approach, and this again has been around for a long time, maybe 40 years. And the idea here is that you use Taylor's theorem. You know, one of my friends who's now a very famous applied mathematician, Mike Shelley, who now works in New York at the Flatiron Institute, he told me once in the mid-'80s, all of non-convex optimization is just Taylor's theorem. That's all it is, right? And Taylor's theorem, of course, is the way that you can get low-order polynomial approximations to a nonlinear function by just expanding in terms of the derivatives. Okay, so for example, f of xk plus d is approximately equal to f of xk plus the gradient transpose d plus 1/2 d transpose the Hessian times d. Okay, approximately equal to that. And so what a trust region method does is it just takes a low-order quadratic approximation to f of xk plus d, and it minimizes that over some ball. Okay, it says, I don't want to move any further, I don't want the d to be any bigger than some delta k, I want to stay inside a ball. So this hk can be the Hessian, it can be the true Hessian, or it can be some approximation. It's usually the true Hessian, right, in practice. Now, this method sort of was out of favor for a long time, but then just recently people have rediscovered it in the context of machine learning. Yoshua Bengio wrote a paper, I don't know, 3 or 4 years ago, where he, dug out the book that I wrote with Nossedal, which has a chapter on trust region, and applied it to some deep learning problem. But the surprising thing about this, people think, you know anything about computational complexity, you've probably heard that minimizing a non-convex quadratic over a box is a very difficult problem computationally. okay? And this can be non-convex. This Hessian here is often indefinite, so it's got negative eigenvalues as well as positive. So in general, the problem of minimizing such a function over a box is very, very difficult. But over a ball, okay, where we use the 2 norm here, so that this is a ball, not a box, that's actually an easy problem. Even if the HK is indefinite, that's an easy problem. And that's still surprising to many people. That's quite an easy problem to solve. And so these methods have generated some interest in the last few years in the context of learning, trust region methods. And for general nonlinear problems, non-convex problems, they're still quite powerful, even for large-scale problems. And then lastly, I'll just mention these cubic regularization methods. These were proposed, well, actually, maybe the first person to propose these was Grievang back in the early 80s, Andreas Grievang. He had a paper which was rejected where he proposed using these methods, and he never published it in the end. But it's still floating around as a tech report. And then it was sort of, the Russians reinvented it in 2006, Nesterov and Polyak, and then some colleagues in optimization have worked very hard on exploring properties of this method for the last few years. And here you take the quadratic approximation, you add on a cubic term. And this function is going to be coercive. As d gets very large, this is going to go to infinity. So you can minimize this function. The trouble is that this function itself is not convex. So it's hard to know how to minimize this. Okay, you have to work hard to minimize this. So that's the difficult part of this problem. Now, there's actually a very close relationship between trust region and cubic regularization. Because if you write down optimality conditions for the trust region, you get something that looks a lot like the cubic regularization. And some people have exploited the relationship between these two to come up with algorithms where, for cubic regularization, that look a lot like trust region algorithms. Okay, so that's an outline of some of the main approaches. They're all fairly classical approaches. I don't think anyone's come up with anything that's radically new, that's different from these. So what we've been working on lately is sort of enhancing these approaches and then trying to prove more stronger complexity results about them. Okay, I just wanted to mention one more, which is conjugate gradient. So I mentioned earlier that conjugate gradient is a momentum type method. But sometimes it's used as part of a trust region or line search method, because if you're, for example, implementing a line search method and you need to compute the Newton direction, that's a complicated computation, right? It looks like you have to find the Hessian and then find the inverse of the Hessian applied to the gradient. That's very expensive computation. So you can state that instead as a solution of a linear system. The Hessian times d equals a negative gradient. So you can write it down as an n by n linear system, okay? Now, if n is very large, it can be very expensive to solve that system, all right? And so that's where conjugate gradient might come in, because conjugate gradient is an iterative method for solving systems of the form AZ equals B, where A is an n by n positive definite matrix. So, of course, you can solve this by directly factorizing A, but that's an order n cubed operation. Conjugate gradient, instead, it's an iterative process. In fact, it's a momentum type method, as I mentioned earlier. It generates a sequence of estimates, Z0, Z1, and so on, to the solution of this problem. This problem, AZ equals B, it's equivalent to minimizing a quadratic function, okay? Because the minimizer of this quadratic function will satisfy these equations. So it's really the same problem. So if you want to implement Newton's method, you can just apply conjugate gradient to the problem of calculating the Newton direction. And the methods that I'll talk about later, that's basically what they do. They solve this system with conjugate gradient. And they've been known for more than 30 years now to be very effective ways of solving large-scale, general, smooth, unconstrained problems. I should mention that this is what we call linear conjugate gradient. Very early on, starting in the 70s, people started to derive nonlinear forms of conjugate gradient that work not just for quadratic functions phi, but for general nonlinear, non-convex functions. And they're quite effective in practice, but usually LBFGS is better. Okay, so I just wanted to point that out. Then there's a little bit of renewed interest in nonlinear conjugate gradient because they don't require much storage. You only have to store a couple of vectors to implement them. And it would be interesting to know if you can prove stronger results about them than are known so far. Okay, so what do I mean by convergence and complexity? So this is one area where the research directions have changed in recent years, because if you look at the classical optimization literature, including my book with Jorge, we typically prove two kinds of results. There's a result that we call global convergence, and by that we mean that if you look at the sequence of points generated by the method, and you look at the accumulation points of the sequence, that's the points where the iterates tend to bunch up, okay, then we try to prove that the accumulation points are stationary. That is, the gradient of f is 0 at those points, okay? So that's not a guarantee that they're local minima, but at least it's a first order indication that it might be a local minimum. Sometimes you can prove more than that. For example, in trust region methods, you can show that the accumulation points satisfy second order conditions. That is, the Hessian is also positive semi-definite. So that's a stronger indication that you're at a local solution. Okay, but typically that's the sort of result that we prove. And the other kind of result we prove is a local convergence result. So in this result you say, let's suppose you start the iterations close to a point x star, which is the solution. It is a local minimum. You show that the algorithm converges at a certain rate. So it could be a linear rate, superlinear, or quadratic. Superlinear, quadratic, all you need to know about that is that they're really fast. Okay. Once you get that rate, you converge to the solution very quickly. All right? So these are the kinds of results we used to prove, but in recent years people have been interested in proving another kind of result, which I'll call a global complexity guarantee. And this is a result that says it gets an overall bound on the number of iterations you'll need to get from the starting point to an approximate solution. Okay? So it's like a global convergence result, except you get a bound on how many iterations you're going to need to get to approximate first order or second order point. And I never cared much about those results historically. The Russians did. Starting in the 80s, the Russians started to prove results like this. And most of what I'll talk about in my talk is basically focused on this kind of result. And the typical result is that, you know, if I start at any point, x0, how many iterations am I going to need to find a point x where the gradient falls below epsilon, where epsilon is a small tolerance, okay? So give me a bound expressed in terms of epsilon, maybe expressed in terms of the problem dimension n, and maybe some other parameters depending on f. How many iterations am I going to need to achieve that, okay? And so nowadays there's a lot of interest in proving these results. The machine learning people really like to prove results like this about optimization methods, partly because there's a lot of influence from theoretical computer science in machine learning, and theoretical CS people love to prove complexity results on algorithms of any type. So it's partly because of that cultural influence that these results are interesting. But it's actually also, it has some practical value because there is some correlation between results, between methods with good complexity guarantees and methods that perform well in practice. So it's not completely divorced from practical experience. So this is why I'm going to focus on these issues a lot in this talk. Okay, this slide is very dense. I'll just skip over it because I'm going to elaborate on these issues a lot later on. But there are these classical practical methods in the literature, and they're all described in this book. Newton conjugate gradient, LBFGS, nonlinear conjugate gradient. I've already mentioned all of those. And they typically have those two kinds of results. Accumulation points are stationary points, and you get some sort of fast convergence to a solution. Local convergence, okay? And then after 2006 in the optimization literature, people looked at cubic regularization and trust region methods and started to prove these global convergence guarantees, and here are some papers that do that. I'll say a little bit more about those later. The Nesterov-Polyak paper was a very important paper in that, starting off that line of research. But as I said, it goes back to a very old paper of Grievunk. And then here's the influence coming in from machine learning. So machine learning researchers who are also doing fundamental optimization stuff now, since 2014, they've sort of come up with new algorithms that sort of are adaptations of accelerated gradient methods, and they do other kinds of things, and they've all proved some sort of global complexity results. And I'll discuss several of these in the talk in a moment. Okay, So I'll give you an example of some very simple classical complexity results. So you can see that the proofs, at least for these simple methods, are not very difficult at all. And they're very simple proofs, so I can fit them on one slide. So here's an example. Let's suppose we're trying to minimize an f, where f satisfies this Lipschitz property. That is, the gradient of f satisfies a Lipschitz continuity property. If I take the gradient at 2 points, y and z, and take the difference of those, then that's less than or equal to Lg, where Lg is some constant, times the difference of y and z. So this tells you the gradient isn't changing too quickly as you change the argument. Okay? So maybe the simplest method for this kind of problem is the so-called short-step gradient descent. So this is where you just get the iterate, xk, you take the gradient of f at xk, and you subtract off 1 divided by Lg times the gradient. Very, very simple method. Okay? And you might ask the question, how many steps do you need to take of this method before the gradient of f of xk falls below some threshold epsilon? All right? So how long do I need to work before I get this inequality? So how big does t is the number of iterations, how big does t need to be to achieve that? Okay, so here's the answer. T, you get that in at most this many iterations. It's 2 times Lg, which is the Lipschitz constant, times the difference between your initial function value and f low. F low is a global lower bound on f. You need to know that f is bounded below. Okay, divided by epsilon g squared. So epsilon g is the tolerance that you're looking for. Okay. So this tells you that in the order of epsilon g to the minus 2 iterations, you'll find a point where the gradient is less than epsilon. Okay? And I'll prove that on the next slide. Very easy proof. So that's for a general non-convex smooth function f. If f is convex, you can say a little bit more. You can say that you can reduce f of xt to within epsilon g of f of x star. That means you're very close to the optimal function value. And the number of iterations you need to achieve that is order of 1 over epsilon. Okay? 1 over epsilon. It's better than 1 over epsilon squared. So if epsilon is 10 to the minus 3, this is order of 10 cubed, 1,000, and this is order of 1 million. Okay? So this is faster if f is convex. You have some additional structure in f. And you can say even more if f is strongly convex. So f is strongly convex means that it's got positive curvature, so it's never flat like this. It's always got a positive curvature to it. And those functions are even easier to minimize. You can get within epsilon of the optimal value much more quickly. In fact, there's a logarithmic dependence on epsilon g. Okay? Epsilon g only comes into the log. Now you've got a factor here, Lg over m. So Lg is an upper bound on the curvature, and m is a lower bound. And so the number of steps depends on the ratio of those two things. So if you've got an ill-conditioned function where there's a big difference between the maximum and minimum curvature, this can be quite a large number. Okay? If you've got a function like x squared where the Lg and m are both equal to 1, then this is very fast. This basically you get convergence in 1 iteration. Okay? But the one important difference here is that if you've got strong convexity, you go from having an arithmetic dependence on epsilon, like epsilon g to the minus 1 or minus 2, to having a logarithmic dependence, and that's a very, very big difference. If epsilon is 10 to the minus 3 here, the log of 10 cubed is only, like how much is that? It's only about 10, right? Rather than 1,000 here. So it's much faster. Okay, so here is the proof of the first result. I'm going to prove this result. And it's very easy. It all fits on one slide. Okay? So first, it uses the fact that you've got an upper bound. If you've got a bound on if the gradient of f is Lipschitz continuous, then the value of f at x plus p is bounded above by a quadratic in p. Okay? Globally, at all points x, and for all values of p, you've got a quadratic upper bound on f. Right? And so a reasonable algorithm, and this is in fact exactly what gradient descent does, it finds the p that minimizes the right-hand side. Because it says if you're minimizing the right-hand side, you're probably getting a good reduction in f of x plus p. And if you're minimizing the right-hand side, this is the minimum. P is minus the gradient divided by Lg. And that's exactly the algorithm that I told you about here. Okay? That's exactly this steepest descent method. Okay? So if you plug that value of p into the right-hand side here, you find that f of xk plus 1 is less than or equal to f of xk minus 1 over 2L times epsilon squared, right? That's what happens when I plug this right in there. And that's true provided that the gradient of f is bigger than epsilon. So if you're not yet at a stationary point, you're guaranteed to get at least this much reduction in the function, okay? So that's the important thing. If you haven't yet achieved approximate stationarity, if you haven't yet dropped below this threshold, you're able to prove that you get a significant reduction in f from each iteration. And you can use that fact. If I just rearrange this inequality, I take the epsilon term over to the left-hand side, I take f of xk plus 1 over to the right-hand side. That's what I'm doing here. And now I'm just summing both sides for k equals 0 up to t minus 1. So if I do that, on the left-hand side I get this times t, all right, because this is just a constant times t, and that's less than or equal to the sum of f of xk minus f of xk plus 1, right? And this is what we call a telescoping sum, right? If I just look at these terms, each term partially cancels the next term in the sequence. And the only things that are left are the f of x0, which is in the very first term, and the f of xt, which is in the very last term. All of the other f of xk's cancel each other out, okay? So you get this upper bound, and of course, if I assume that f is bounded below, then f of xt is bigger than f low, the lower bound on f. And so this is bounded by this, right? So all I do is rearrange this expression. I want to get a bound on t, the number of iterations I need to fall below the threshold. I just take this stuff, I leave t on the left-hand side, and take everything else over to the right-hand side, and I end up with this result, right? So this is how many steps I'm going to need to get the gradient below the value epsilon g. Okay, so that's the proof. And these other proofs for these other results are not a little bit more complicated, but they still fit on one slide. And I'm not going to show you those, but you can easily find them in some textbooks that we've been writing. Okay? So these are basic complexity results, and many of the results I have subsequently have this flavor, where we try to find a power of epsilon that gives you the upper bound on the number of steps. Okay, so what about momentum methods? What sort of complexity properties do they have? Their results are a little bit better. Yeah, I'm just looking ahead a little bit. So here are some examples of momentum methods. These are the ones where you mostly keep moving in the same direction that you've already moved in, but you apply a little bit of a modification that brings in the latest gradient information. So maybe apart from conjugate gradient, people didn't seem to realize conjugate gradient was a momentum method until fairly recently. And conjugate gradient has been around since the 1950s, I think. It's a very old method. But the Russians invented heavy ball sometime maybe in the 70s. And in this method, you just take a gradient step here, you take the momentum part here, and you choose a constant alpha and beta. Usually the beta is close to 1, a little bit less than 1, and alpha is very small. It's like 1 over L again, just like in the short step steepest descent. So that's the heavy ball method. But Nesterov invented this method that's become very famous in the early 80s. And the only difference between Nesterov and heavy ball is that you evaluate the gradient at a different point. That's why I've highlighted it in red here. In Nesterov, you actually take the step to xk plus beta times xk minus 1. You take that step first, and then you evaluate the gradient at that point, right? And then you use that gradient in this formula to get the step. So it's very similar. It uses the same amount of work. You only need one gradient evaluation at each step. And again, you use these values of alpha and beta. And Nesterov has these very nice ways of computing. He changes alpha and beta at each value of k. He has a very beautiful way of doing that. And he ends up with similar convergence properties, but in practice, it behaves better than heavy ball. Okay? You can actually rewrite Nesterov. Most people that implement Nesterov, instead of just having a single sequence xk, you can have two sequences, xk and yk. But the yk is just the thing inside the brackets here. So you just define yk to be this thing in red, and then you evaluate the gradient at yk, and you get the next value of x by just taking, yk minus alpha times the gradient at yk. Okay, so you can implement it using, this is equivalent to this, basically, same thing. It's just better from a bookkeeping point of view. Okay, so what sort of result do we get for accelerated momentum methods versus original gradient methods? Well, when you apply them to strongly convex functions, you definitely get an improvement. Remember, for strongly convex over here, we had this logarithmic dependence on epsilon, but we also had Lg over m, the ratio of the upper bound on the curvature to the lower bound. So in the Nesterov accelerated methods, instead you have the square root of that ratio. Okay? So if that ratio is like, 10 to the 4, if you've got an ill-conditioned problem where there's a big gap between maximum and minimum curvature, in steepest descent, it's going to take order of 10 to the 4 log epsilon iterations. In accelerated gradient, it's only going to take order 10 squared log epsilon iterations. So for ill-conditioned problems, it's much faster, okay, to do it that way. So that momentum idea, very effective in theory and also in practice. If you've got a convex F where you don't have strong convexity, this function might be flat in some places. Again, you get an improvement. For steepest descent, you get 1 over epsilon. For accelerated gradient, you get 1 over square root of epsilon. So again, if epsilon is like 10 cubed, this is 1,000, and this is about 300. This would be 1,000, and this would be about 30. Okay, so much less. Okay. And as I mentioned, conjugate gradient, it's also a momentum method. It also has a very rich convergence theory, but the convergence for conjugate gradient is mostly for the special case where f is a quadratic. Okay, then it's got a very strong convergence theory, but beyond quadratic, you can't say much about conjugate gradient. Okay, so let me talk a little bit about escaping saddle points. So this is the big problem when we're doing non-convex optimization, is we might get stuck at a point where the gradient is 0, but it's not a local minimum. And so is it possible that these gradient methods will get stuck at a saddle point? If you have an iterate that's at a saddle point, it'll just stay there and never move away, okay? And that would be a bad property. So the answer is yes, these methods can get stuck at saddle points, and it's very easy to see that. If I define a very simple function, I've actually got a picture of it on this slide. It's really hard to see what's going on. But here's the function. It's a function of 2 variables, and it's equal to x1 squared minus delta x2 squared, where delta is a small positive constant. So in the x1 direction, it looks like bowl-shaped. It's convex, right? But in the x2 direction, it's like upside-down bowl, okay? It's got a curvature of minus delta, or minus 2 delta. But the delta, delta might be small, so it might be a very shallow bowl. Now, if you start from this point, 1, 0, somewhere along the x1 axis, and you apply a gradient descent, it's just going to move to the 0 point and stop. Okay? It's not going to be able to move away from 0. And that's not a solution. 0, 0 is not a solution. Because if you move away from 0, 0, in the x2 direction or the minus x2 direction, the function is going to go negative, right? It's going to keep decreasing. So this is bad behavior. You don't want this to happen. And it can happen. It's possible that this might happen for these methods that I've talked about so far. But it's very unlikely, okay? It's very unlikely in that it only happens if you start with a point where the second component is 0. If you start from any point where the second component is slightly positive or slightly negative, it's not going to get stuck at 0, okay? So there's this paper by Lee et al. From 2016 where they show that for general functions, not just for quadratic non-convex, but for general non-convex functions, you're never going to, you have to be extremely unlucky to get stuck at a saddle point. You have to start at a very special set of starting points on a low-dimensional manifold. So, and you can see that even here. If you just choose a random x naught, the chance of the random x naught being right on the x1 axis is 0, right? You have to be incredibly unlucky to get a random point that's on the x0 axis, okay? However, you can still ask the question, how long does it take to escape from a saddle point? If you're using a steepest descent method or an accelerated gradient method, how many iterations does it take before you move away from a saddle point and keep going downhill? And we explored that question a couple of years ago, a paper with Mike O'Neill, and we did some experiments here, and this is the function that I just talked about. So here's the 0, 0 point. It's a saddle point, and the function keeps decreasing in this direction. So these are the contours of the function, these colored lines. and it increases in this direction, decreases in this direction. So if I apply steepest descent starting from this point here, it moves very close to 0, 0, and then very, very slowly it moves away along the x2 axis. But it takes a long time to escape from the saddle point, many iterations, right? So if instead we apply the heavy bore method, which is an accelerated gradient method, the blue crosses are the iterates of that method. So you can see that they bounce around a lot, but generally they escape much more quickly, okay? Within 10 iterations of the accelerated method, you've already escaped to this point, whereas you've needed, 40 iterations of steepest descent to get to that point. So the divergence is much more rapid. So that's another way in which accelerated gradient methods have an advantage over steepest descent methods. Now, if you apply accelerated gradients to non-convex functions, you can't prove very much. All of the theory for accelerated gradients, almost all of the theory, is only for the convex case. But this says that if you apply them to the non-convex case, they can still behave quite well, okay? All right, and this is another graph, and this is how many iterations it took to escape from the saddle point. This is the gradient descent method. It's taking, 700, 800 iterations to escape, and these are different momentum methods, and within less than 100 iterations, they've already escaped. Okay, so they escape much more rapidly. Okay, so going back to the start, I'm now going to talk about different approaches that people have proposed and studied recently for non-convex optimization. So what I'm looking for, first of all, is a point that satisfies approximate second-order necessary conditions. So these are sort of indications that I might be at a local solution. They're not a guarantee, but they're indications that I might be at a local solution. So first of all, you want the gradient to be 0. Second, you want the Hessian to be positive semi-definite. Okay? And so we're looking for points that approximately satisfy these conditions. In fact, I think I've got it on the next slide. We define some tolerances, epsilon g and epsilon h, and we say I want the gradient to be less than epsilon g, and I want the Hessian to have all its eigenvalues bigger than minus epsilon h. So they might not all be non-negative, but at least they're not very negative. They're only very slightly negative. Okay? So we look for the number of iterations that you need defined in terms of epsilon g and epsilon h to achieve these properties here. Okay? And I'm going to assume for most of this discussion that not only is the gradient Lipschitz continuous, which is the property we had earlier, but also the Hessian. I want that to be Lipschitz continuous as well. Okay? And given these properties, I'm able to define these global bounds on the number of, on the function. So this one I already had earlier, where I got a global quadratic bound on f. But if I've got this property where the Hessian is Lipschitz continuous, I also get this global cubic bound. And these bounds are very useful in designing algorithms and helping you prove things about them. Okay? So we're looking for points that satisfy these properties, as I said. And there are different ways to measure the complexity. One is to look at the number of iterations it takes to satisfy these bounds. But the other thing you can do is to look at how much work do you need to do. And the reason that's important is that different algorithms, the cost of doing one iteration can be very different between different algorithms. Some algorithms like steepest descent, it's very cheap. You just have to evaluate a gradient. But other algorithms like cubic regularization, you have to evaluate a Hessian, you have to solve a difficult cubic optimization problem, you have to do a lot more work, right? And so we're also interested in measuring what we call operation complexity, which is the number of, basically the amount of work you have to do to achieve this property here. So that's another way to measure complexity. Okay? All right, so I want to talk about, first of all, a very basic method that can achieve these properties here, okay, in a reasonable number of iterations. So I've already told you about a steepest descent method that achieves this property. So I'm now going to tell you another method, which is a little bit more complicated than steepest descent, that guarantees not only this property, but also this one, okay, nearly positive definite Hessian. And it's a very simple approach. It just takes two kinds of steps. First of all, if the gradient is bigger than epsilon, it just takes the steepest descent step. We've already done that, right? We already looked at that algorithm. And you do that if the gradient's bigger than epsilon. But if the gradient is smaller than epsilon, Then you want to look at the second derivative to figure out if it's positive definite, right? So if the gradient's smaller than epsilon, you look at the Hessian, you look at the eigenvalues of the Hessian. If the smallest eigenvalue is less than minus epsilon h, then what you do is you find a negative curvature direction. You find a direction dk basically it's the eigenvector corresponding to the most negative eigenvalue, okay? And you use that as the search direction, all right? So this actually takes a lot of work. This is an order n cubed operation to find this. So we'll talk about that more later. But let's assume you can find that direction. You take a step along that direction of this step length. It's 2 times the absolute value of the most negative eigenvalue divided by LH, okay? You take that step length. What you're able to show using some argument here, which I won't go over, but this argument is based on the cubic upper bound, on this upper bound here. You just plug in this value of p into this function, and you can show that you get this much improvement in the function. Between f of xk and f of xk plus 1, you get at least this much improvement. 2 times epsilon h cubed, where epsilon h is the tolerance here, divided by LH squared, okay? This much improvement. And so you can show that for either kind of step. If you take this kind of step, you get this much improvement. If you take this kind of step, you get this much improvement. So in every iteration, you're at least getting this much improvement in f. You're at least making a certain amount of progress, okay, towards finding the minimum. And so to turn that into a complexity, we just say, you know, we start out at f of x0. We know that the function is lower bounded by f low. We know that we're making at least this much progress on every iteration. So the total number of iterations that I need is just f of x0 minus f low divided by this. Okay? That's going to give me an upper bound on how many iterations I'll need. That's all it is. Very simple idea to get a complexity. And this is what I end up with. It's just order of epsilon g to the minus 2 and order of the maximum of epsilon g to the minus 2 and epsilon h to the minus 3. Okay? So that's an upper bound on how many iterations you need. Okay? Now, that's a very simple algorithm. All the analysis basically fits on 2 slides. All of the other algorithms that we come up with have a slightly better complexity. Instead of epsilon g to the minus 2, they're able to get epsilon g to the minus 3 over 2, which is a little bit less, okay? But in order to get that improvement, you have to take much more elaborate steps. You have to take, well, I said it's not too much more elaborate, but in the full generality, it becomes quite significantly more elaborate. But you have to use Newton steps. You can no longer use steepest descent steps. You have to use Newton steps. And that gets this improved complexity, okay? Now, as I mentioned here, I'll take a break in a moment, but as I mentioned here, this is expensive to implement because we need to find the most negative eigenvector. And so one of the things I do in the rest of the talk is come up with a way of finding this approximately, finding the dk approximately, that's less expensive. You can apply a method called the Lanchos iteration, which is an iterative method. It's very similar to conjugate gradient. It's an iterative method for finding the most negative eigenvalue. And then the amount of work you have to do to find dk can be much smaller. And so we have an approximate version of this method that has a better complexity analysis. Okay?